All right, so we're going to finish up chapter 4 today, which is on radical functions. So we've studied, this week we studied rational functions, looking at solving them. Last week we studied graphing rational functions. And now we're finishing up with radicals. So we're going to look at kind of the things we always do. How do we graph? How do we solve the equations? And how do we do transformations? The transformations are going to be exactly the same as everything we've done all year. We'll make sure we remember what those are. These are both examples of radical equations. Yes?
I'm gonna move to like the middle because
Yeah.
the glare of the shower curtain keeps messing with my eyes.
Okay. Yes. So basically, any expression that has this symbol in it, this root symbol, that's called a radical. And this number that we put in like that little check mark part of the radical, that's called the index. That basically tells you what kind of radical you're doing. Is it a square root? Is it a cube root? Is it a fourth root? What is it? The key is that the index, though, has to be an integer greater than 1. There's no such thing as like a 1.5 root. Okay, we don't do decimal roots. You can do square root, you can do cube root, nothing in between. All right, in order to be a radical. So again, n is called the index. This whole thing is called a radical expression. The number that is underneath the radical sign, that is called the radicand. The radicand just means the thing you're taking the root of. So like if I did this, I would say my radicand is 4. That's the thing I'm taking the square root of. And then the actual like check mark thing with the horizontal line, that symbol is called your radical sign. Okay, so just going over some of the vocabulary. Okay, any questions on radical, index, radical sign, and the radicand? Any questions on those terms? So when you write a radical sign, if you don't put in an index, we always assume it's a 2. So when you do this, I'm assuming you mean that. You don't have to put the index in if you want it to be a square root. Now, rational expressions like this, or radical expressions, can also be written without a square root sign. Okay, there is a way that you can use an exponent to represent a root. And does anybody have a guess what exponent would represent a square root? Like instead of writing this, I could write this. And I'm looking for what power you could put right there that would mean the same thing. Yeah?
The 2.
So what's the square root of 9?
3.
3? And what's 9 to the second power? Are they the same? No. So it's not a 2, but it does have something to do with a 2. Yep.
1 over 2?
1 over 2. Good. So if you have a square root, it's the same thing as writing it to a 1/2 power. We're going to see more of that when we study logarithms in chapter 5. But for now, we're just kind of reviewing it. And the trick is, you basically put it, the power, as 1 divided by your index. That's the exponent. So what do you think a cube root would be? What power, Tyler?
Would be 1/3.
That would be to the 1/3 power. And you can try it on your calculator, pick a number, take the cube root of it, and then raise that same number to the 1/3 power. It's the same thing. And now, how about this one? We have x, the fifth root of x to the fourth. What's going to be my exponent when I do a fifth root? Matt?
1/5.
Yeah, it's going to be 1 over 5, and this is one that we can actually simplify a little bit more. It's x to the fourth, and now you're raising it to the 1/5. That's a power to a power. What do you do when you have a power raised to another power? Yeah.
Multiply.
So what would the final exponent be in that one?
4/5.
4/5. Yeah. So that's one reason why you might do something like that, because it allows you to simplify it a little. Okay, so any questions on writing a radical as a fractional exponent? All right. So let's talk a little bit about what it means to solve a radical equation for a principal root. First of all, a principal root means they only want one answer. We know from solving like square root problems, for example, there are two. Right? If you take the square root of 4, you get 2 and -2. But when they talk about the principal root, they only want one answer. So I'm going to break this up into two cases. Are you dealing with an even root or an odd root? And I'll show you what you do. If you're dealing with an odd root, you're basically trying to solve, you must be solving an equation like this. So let me give you an example. X cubed equals 64. If you were trying to solve that equation, you would have to take the cube root of both sides. And you'd have something like this. So if you're trying to solve an equation in this format, you would have to take a root on both sides to get rid of that exponent. Now, if the root you're taking is odd, all you have to do is basically plug that in on the calculator, and it'll tell you what the cube root of 64 is. Okay, if we try it, math, 4, do it on the home screen, math 4, 64, it tells me the answer is 4. Now, how about if I did the cube root of -64? Is there a number that I can multiply by itself 3 times and get -64? Yeah, Ethan? -4. Yes. So what I'm kind of getting at here is when you're doing odd roots, you can do a positive number or you can do a negative number. You can take an odd root of any number that you want and it will work fine. Positives, negatives, or 0. I don't know why people think, well, it can't be 0. You can take the square root of 0, that's no problem. You can take the cube root of 0, that's no problem. 0 is perfectly fine to use with roots. I think people mix that up with putting 0 in a denominator. That's different. Okay, so odd root, you pretty much just plug it in and you get your answer. Now, with an even root, there is a restriction on the kind of numbers you can take roots of. It's not like odd roots, okay, where you can take the root of anything. Let's pretend like there wasn't a restriction. Let me pick a number for a that wouldn't work. Let's try -5. X squared equals -5. What would you do on both sides to solve that equation? Jake?
Square root both sides.
You'd square root both sides and you'd have this. What's going on there? Square root of -5. If we tried to simplify that, what would happen? Sarah? Yeah, we'd have an imaginary number. We don't want to get into imaginary numbers. That's why I'm putting this restriction here. By doing that, I'm guaranteeing you will never have an imaginary number in this problem. So a always has to be greater than or equal to 0. And that's not just true for a square root. It's true for any even root. Square root, 4th root, 6th root, 12th root, any even root. So let's look at one we could actually do. Let's say x squared equals 36. If I ask you to solve this problem for the principal root, you take the square root of both sides. And you might be thinking, well, he taught us that the square root of a number has 2 answers. And you're right. But if I specifically ask for this, I only want this. I don't want both answers. So what is the answer to square root of 36 that's not negative? I know negative 6 is an answer. I don't want that. Ashley?
6.
6. Okay. That's all you have to do. So if you see a problem in the homework and it's asking you to do an even root, and the number on the other side is negative, you can just write no solution right away. It's not solvable. All right, let's take a look at this. See what I did there again? Getting crazy with the fonts.
You had fun making these songs.
All right, so what I want to see what happens here is when you take the square root of a number, I want to see if it does it get smaller or does it get larger. Let's try 4. What's the square root of 4? Yeah. 2. So what happened that time? Smaller or larger? Yeah. Okay, that got smaller. Let's try square root of 18. So second, square root 18. Okay, 4.24. That's smaller. Can anybody think of a number I can take the square root of and it doesn't get smaller? Yeah, Matt?
1.
1? Yeah, there's actually one other number you can take the square root of and it stays the same. But 1 is an answer. That's the one I think I wrote down. And yeah, Jake?
0.
1 and 0. Those are 2 numbers you can take the square root of and they stay the same. So the square root of 1 stays the same. The square root of 0 stays the same. What happens if you take the square root of numbers between 1 and 0? But we can't go negative. That's imaginary. Like, let's say you took the square root of 1/4. What times itself gives you 1/4? Yep. 1/2. What happened in that case? We started with 1/4, we took the square root of it, we got a half. My number got, Tyler?
Bigger.
Got bigger. It got bigger when you did that. Same thing would happen here. If you took the square root of 0.5, you can see again it gets bigger. 0.71. So what I'm trying to show you is when you take the square root of a number, does it get bigger or smaller? The answer is it depends. Is your number bigger than 1, equal to 1, or less than 1? So let's take a look at 2 square roots. Let's take a look at, oh no, I'm sorry, not 2 square roots, just 2 roots. Let's look at the square root of x, and let's look at the 4th root of x. Not sure if we've talked about it, but this would probably be a good time. You don't have a button on the calculator for anything above cube root. So if you want to type in a 4th root, you have to press 4, math, option 5. That's how you do a root other than 2 or 3. Put your index in, then go to math, option 5, and it'll change your index into a little number that looks like that. All right, so let's do a zoom 6 and just see what it looks like. So there's a very typical even root function. They all kind of have a curve that goes to the right. And you can see they don't go to the left unless you flip it. You could flip it. But if you don't flip it, it goes to the right. Now, I don't know if you can really see what's happening, but I want to look at which one is on top. The blue one or the red one? Well, that's kind of like asking the question when you take the square root. Is it smaller or larger? Well, it depends. Depends on where you're looking in the graph. Let's zoom in on the section that's 0 to 2. And I think you'll be able to see what's happening here. So let's go 0 to 2. And on our y, let's go 0 to 2. That's your square root. That's your fourth root. So notice what happens when you go past 1. The fourth root gets smaller than the square root. When you get after the number 1, the fourth root is smaller. But before that, the fourth root is actually larger, between 0 and 1. Okay, so it's kind of weird, but that's what happens. The behavior switches at 1. And if you did a sixth root, that would probably look something like this. That would be on top of all of them. Well, it never goes down, but it would curve up and do something like that. It would stay above them, but then after a certain point, it would go under them. Okay, but notice they all increase. They never get flat. They do keep going up as you go to the right. And does anybody see a point that the square root and the fourth root both go through? It's actually 2 points. Ethan?
Excuse me?
Do you see a point?
Of which they both go through? 1.
1 comma...
1.
Yep, I agree, 1, 1. And does anybody see another point that they both go through? Yep. They both go through 0, 0. In fact, those are points that are common to all even roots, unless you transform them. Okay. So 0, 0, 0 is a point. 1, 1 is a point. Now the domain and the range. Let's go back and look at the picture. Domain is how far left and right the graph goes. Range is up and down. Look at this. It's probably easier to look at this one. This graph starts at the origin, and it's going to head that way forever, and it's going to head that way forever. It's never going to go, it's going to always stay in quadrant 1. So that means it goes to infinity on the x-axis, and it will go to infinity on the y-axis. And you can include 0. I don't know how to say that any differently. It's fine to include 0 when you take a square root. That's okay. You can do that. So you can take the square root of 0. Okay, you can include 0. Right, so any question on the general look of an even root function? Even root functions have what I'm going to refer to today on the test as a starting point. They start and they curve in one direction. Okay, that's the general look of an even root. Okay, so that's the general look of an even root. Now we're going to take a look at an odd root. First, I want to remember, was there any restriction on what you can plug into an odd root? With evens, we could only take positive numbers, greater than or equal to 0. Was there any restriction on odd roots? Oh, Bailey? So when we plug a number into an odd root, did I write down that there were any restrictions?
Oh, no.
No. So what that means about odd roots is they're not going to go just in one direction, like an even root. They're going to go both directions. So let's take a look at what an odd root looks like. Okay, I'm just going to graph one. Let's do cube root. So I'll just change my index to a 3. And I need to do a zoom 6. And you can see that this is what an odd root looks like. These type of graphs have what I call a center point. They don't have a start point. Start means they start somewhere and they go one direction. This type of graph has a center. And in that one, it's at the origin. All right. And let me graph, let me throw one other root on there. Let's do, that's a cube root. Let's do a 5th root. And I want to see if you can tell a couple different points that are common to all of them. Okay, you might be able to see one of them there. Anybody? Maybe let me zoom in. And then I think you'll be able to tell pretty clearly. They're going to have 3 points. All odd roots have 3 points. They all cross that. Anyone think they can see the 3 points? Or just one of them? Yeah.
0, 0.
Yeah, all odd roots will go through 0, 0. They will all go through, yep.
-1, -1.
-1, -1. And they will also all go through, yep.
+1, +1.
+1, +1. Those 3 points are common to all radicals with odd indices. Domain and range is a little bit different on odd roots. Odd roots are going to go left and right forever, and they'll go up and down forever. So the domain and range is all real numbers. It might look like the odd root is starting to level off, but it never does. It will very slowly just kind of keep going down like that, just very slowly. So again, odd roots, center point. Even roots, start point. Okay, that'll be a question that I will ask you on the test. All you have to do is look at the index. If it's even, it goes in one direction. If it's odd, it has a center, and it goes in both. So if you look carefully at the even roots and the odd roots, the center and the start point is always the origin. If we go back and look at these, the center point is the origin. And if we go back and look at these, the start point was the origin. The only way that you can move that is if you transform it. And we'll look at transformations in a little bit. I think that was it. A little bit is right now. So there is how a transformation could look. Okay, the A, the B, the C, and the D. Remember, 2 of those letters are going to do shifting. 2 of those letters are going to do stretching. We just have to identify which ones are which. Also, 2 are horizontal and 2 of them are vertical. The first one, and I use the letters A, B, C, D because that's the order you have to look at them in. The first one is adding, or it could be subtracting. Could be either one. Adding or subtracting inside the radical. Does anybody remember what adding or subtracting does when it's inside the function? It would be the same thing if you had a parabola and you did that. That's adding inside. Yep.
Moves it left or right?
It will move it left or right. So that's your horizontal shift. We've written this in detail before, but can anybody remind me if you have a plus, which way does that move the graph? Tyler?
Left.
Left. That's important. It's the opposite of what you would think. Plus moves it left, a minus would move it to the right. All right, let's do B. B is still inside the radical, but it's multiplication instead of addition or subtraction. What kind of transformation is B? Yeah?
Stretch or shrink.
It's going to be a stretch or a shrink. What type? Horizontal or a vertical?
Vertical. Horizontal.
Well, it's going to be horizontal because we're still inside the function. Anything inside is horizontal. So that's going to be a horizontal stretch. Again, it's backwards from what you would think. If you put in a number like this, that is a horizontal stretch, but it's actually a horizontal stretch by 1/3. When you put in a big number, it actually compresses it down. If you put in a small number actually makes it bigger, stretches it out bigger. So it's the opposite of what you would expect. This, if you were to graph it, would actually be a horizontal stretch by a factor of 2. This one is a horizontal stretch by 1/3. So it's the opposite. All right, how about C? That's multiplication again, like B, but it's on the outside. So what's C going to do? Yeah?
The vertical stretch or shrink?
That's a vertical stretch. And that's exactly what you would expect. A bigger number will stretch it bigger. A smaller number will compress it smaller. And how about D? D is adding and subtracting again, but now we're on the outside. Tyler?
Is it the vertical shift up or down?
That's your vertical shift. As you would expect, positive is up, negative is down. Now, one thing we didn't mention, but I think we've mentioned before, if B or C had a negative in front of it, what would that cause your graph to do? That would be another transformation. Jake?
Be a reflection.
That would be a reflection. If B is negative, it's a horizontal reflection. If C is negative, it's a vertical reflection. And just to be clear about what that means, this is a horizontal reflection. That's a mirror image over the y-axis. Vertical reflection, that's a mirror image over the x-axis. So you can say it either way. But that's what the A, the B, and the C would do. So I said here that it's similar to transformations we've studied in the past, and you're going to learn when we start trig, it's similar to trig transformations as well. We have a few different names we use, but the idea is exactly the same, adding and multiplying, whether it shifts or stretches. So what I want to do in this one is tell me how you would get g of x from what we call the basic graph, or sometimes they call it the parent function. So what would you have to do to square root of x to turn it into square root of x minus 2? Well, Zach?
Shift it right 2 units.
Shift it which way?
Right.
Yeah. So you would shift square root of x right 2 units. And that's how you would get g of x. All right, let's try this one. H of x equals square root of x plus 3. Somebody else tell me how you would get that one.
Horizontal shift left and right.
So you would shift the square root of x left 3 units, and you would get h of x. Now, what's kind of strange about k of x? What looks different about that one? Compared to the other two and compared to how I wrote it with the A, the B, the C, and the D. Yeah?
In a different order.
It's in a different order. We should always put it in this order when you're trying to figure out transformations. So the X term first, the one without the X comes after it. Abigail, how could I rewrite that so my X term is first?
Negative x plus 3.
Yep, we're going to write negative x plus 3. Now there's two transformations happening here. What would I have to do first to change that into that? What's the, Jack, what's the first transformation you would do?
Horizontal shrink.
Can you say that again?
A horizontal shrink.
So you're looking at, you're saying we have a number there for B? Because that's your horizontal stretch or shrinking?
Yeah.
We don't really have a number there. We have a negative sign there, which we do have to deal with, but that's something else. Francesca?
Shift left 3 units.
The first thing you'd do is you'd say, okay, do I have a number for A? Yes, I do. It's a plus 3, so then I have to think, all right, plus moves it left. So shift left 3 units. Now we want to deal with that negative. What's that negative going to cause the graph to do, Ethan?
A reflection.
What kind?
Or a vertical one. To go over the x-axis.
What you said was consistent. A vertical transformation is, a vertical reflection is over the x-axis, but that's not what happens here. That's where the B is, right? Think about what kind of transformation B is. Is B a vertical type of transformation?
No, it's a horizontal.
Yeah, it's a horizontal. So that negative is a horizontal reflection. A vertical reflection would be if you had something like that. If you put the negative in front. Okay, any questions on that? That's the transformations. How about with a graph like this? Center point or start point? Which one? Yeah.
Start.
How come?
Because it's not like cubed.
So can you say what it is instead of what it isn't?
It's a square root.
It's a square root. That's an even indexed root. Even index, start point. All right, so let's look at doing a few sketches. So whenever we want to sketch one of these graphs, you always want to include the point that would have been at the origin. For an even root, that's a start point. For an odd root, it's the center. So to figure out the coordinate that corresponds to 0, 0, you have two things you have to find. You have a new x and a new y value if you do a transformation. If you don't do a transformation, then nothing happens to it. But if you do, this is how you find the new start/center point. Same way for both. To find the x value of that point, set the radicand equal to 0 and solve. And remember, the radicand is this. Set that equal to 0 and solve. And then, once you know the x, well, you're going to have something like this. once you set the radicand equal to 0 and solve, you're going to know the x value. Then all you have to do is take that number, plug it back in, and do it out, and you'll have the y value. So to find the y value, substitute the x value back in. But the substitution should be very simple if you did that part correct, because you already know what you're going to get when you plug it back in, at least right here. And if you don't get 0, then you did something wrong. But let's try an example. Okay, so yeah, the other thing you'll need is that'll give you 1 point. You're going to need a few more points to do your sketch. If it's an odd root, then it is okay to check points in both directions from the center. If it's an even root, you only want to check points in one direction. Which direction? Whichever direction doesn't give you imaginary answers. If you go the wrong way, you'll get imaginary y values. No good. All right, so let's try sketching a cube root. Now, before we do it, just think about it. Is this going to have a center point or a start point? Jake?
Start point,
Why?
because it's a odd number.
So it's going to have a start point because it's an odd
Oh,
number.
and then midpoint.
Yeah, it's going to have a center to it. So when we graph this, we're going to find the center, and then we're going to check points on both sides to get that curve. Okay. First thing I need to do is find the center. So I take my radicand, and what am I supposed to set it equal to? To find the new x value of my center. Yep,
0.
you're going to set it equal to 0. So just added the 2x to both sides. And Casey, my last step there would be divide by 2, divide by 2. So Matt, what's my x value? Let's just do it as a decimal because we're going to graph it.
1.5.
Yep, so my x value is 1.5. Again, this is just 1 point I'm going to use, but it's an important one. It's the center. And now, to get the y value, plug that back in. And we use substitution. What's 2 times 1.5? Tyler? 3. And what's 3 minus 3?
0.
0. And what's the cube root of 0?
0.
What's 0 times 2?
0.
We should have known that this whole part was going to come out to 0 because that's what we initially picked 1.5 to make happen. Right? That's why we have 1.5. This whole part comes out to 0 plus 1. So that is usually your y value. Everything else should come out to 0. All right, so that's 1 point. To get some other points, we're going to use the table just because that's quicker. All right, so I need to type in 2 times the cube root. You're going to have to do that like this. 2 times 3 math 5. That's one way to do it. 2 times the cube root of 3 minus 2x. Don't forget your plus 1, but make sure you are outside the radicand. Now, what I like to check on the table is let's check the center. Make sure 1.5, we get 1. I don't know if you can see it, but we do. And let's check some other points. I don't know if I'm going to use those or not. They were just in there already. My graph paper goes -10 to 10. So try to pick some points on each side of 1.5. Let's do 3, 5, 8, 10. I just random. And let's do -3, -6, -8, -10. That's probably more points than I need. But I'll graph those points and we should see a nice cubic function. All right, so let's get some graph paper. All right, so 1.51, that's going to be my center. Let's see. 3, roughly -2, a little above. All right, 5, a little above -3. 1, 2, 3. Okay, -6, roughly. Oh, I'm sorry, I'm looking at the wrong one. Let's do 10. 10, a little below 4. 1, 2, 3, 4. That's enough. I can see the curve. If you need more, you can do more. -3, we're a little above 5. 1, 2, 3, 4, 5. -6, roughly. 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And let's jump to -10, a little over 6.5. 1, 2, 3, 4, 5, 6.5. Okay, I can see the curve there. So it's going to kind of come down, curve, and keep going. And that's how you graph a cube root. Now, I'm not going to go through this one, just I'm going to ask you a couple questions. Center point or start point here? That is a start point. And to find it, you would set that equal to 0 and solve. You get an x value of 4/3. You'll get a y value of -2. Now, Bailey said it has a start point. The x value of the start point is 4/3. You can only plug in numbers in one direction. Either the number's bigger than 4/3 or the number's smaller. Let's pick a number bigger than 4/3 and try it. Somebody give me a very easy number that's bigger than 4/3. Not a fraction, just a nice, no decimal. Yep. 2. Let's try plugging in 2 here and see what happens. What's 3 times 2? Yeah. And 4 minus 6?
-2.
And the fourth root of -2. You can't do that. You went the wrong way. Okay, we went the wrong way. We can't pick numbers that are bigger than 4/3 because we're going to end up with imaginaries. When you're graphing this one, pick values smaller than 4/3. I would probably pick 4/3, maybe 0, -2, -6, -8, -10. That should be enough. Also, this negative is going to cause a reflection. Instead of your graph going this way, it's going to go that way because it's been flipped. Okay, but it will curve to the left. And that would be the idea of a fourth root. Fourth root, sixth root, eighth root, 10th root, it doesn't matter what index you use. They're all going to look pretty similar. Okay? It doesn't really change the graph a lot. Maybe just the steepness of the curve a little bit. All right, and the last thing. So we looked at the transformations, we looked at the graphing. Now this is the algebra part where we solve radical equations. Some radical equations are pretty easy, some are a little harder, depends. Generally, the less radicals you have in the problem, the better off you are. But the goal is to isolate a radical on one side and then get rid of it. You get rid of it by raising it to a power that would cancel it out. So what do I mean? If you had a problem like this, that has a radical isolated on one side, I would square each side because squaring would cancel out a square root. If that was a cube root, I would have to cube each side. And the more radicals you have in the problem, the more times you have to raise each side to the power. I would never give you one that you would have to do it more than twice. Because it starts to get kind of bad. You do have to check for extraneous solutions, okay, just like we did yesterday. we'll start with one that's pretty easy, and then we'll do one that's a little harder, or at least get through maybe the first step or two of it. Let's try this one. All right, do I have a root that is by itself on one side already? Tyler?
You have X.
Is that a root? X. No, I'm looking for whether or not I have a root by itself. Do I have that right now? With nothing outside the root on the same side. We'll give it again. We're going to do one like this, and then we're going to do one like that. That's different. So I'm going to ask you, does that have a root by itself on one side? Compared to, does that have a root by itself on one side? What do we think about this one now? Ethan?
It does.
It does. It already has a root by itself on one side. That one doesn't. You'd have to move one to the other side first. But this one does. So what power could we use? You have to do it on both sides. That would get rid of a cube root. Yeah.
Cube each, both sides.
Yep, we're going to cube both sides. And that's going to give me x squared minus 2x plus 2 equals x cubed. Now we have 4 terms there. Does anybody remember the kind of factoring that we try to do when we have 4 terms? Special kind of factoring, yeah? No, it's a kind of factoring. So it's like factor by something. But sometimes we have to use synthetic division when we're solving for roots and getting it equal to 0. I'm going to hope we don't have to do synthetic division and rational root theorem. That would be a mess. We won't, don't worry. Yep. We try to do factor by grouping. If that doesn't work, then yes, you'd have to go through rational root theorem, synthetic division, quadratic formula. That'd be a mess. But that's not really the focus of what we're learning today, so probably not going to be that bad. So to do factor by grouping, you get everything on one side, which I've just done. I moved everything to the right. And factor what you can out of the first 2 terms. What factors out of x cubed and x squared? What do they both have in common? Yeah, okay. How about Sarah?
X squared.
Yeah, they both have an x squared in common. And if you factor that out, you'll be left with an x minus 1. My goal is to get x minus 1 again. If I do, then I can use factor by grouping. What can I factor out of the last 2? Yeah.
2.
2. And what am I left with if I do that? Yeah.
X minus 1.
I'm left with x minus 1 again. This is perfect. It's going to factor out very nice. So now, factor the x minus 1 out of each term. We're pulling that out in front. If you do that here, you're left with an x squared. If you take the x minus 1 out of the second one, all you're left with is a plus 2. And now we just have to set each factor equal to 0, just like a quadratic, and solve it. What would make this first factor 0? Ashley? 1. Now the second factor you don't have to worry about, because look at what would happen if you set the second factor equal to 0. You'd have this. And what kind of answer would that result in?
Imaginary.
That'd be imaginary. If that hadn't happened, like if this was x squared minus 2, we would have been okay. But it resulted in an imaginary, so I don't have to worry about it. So So it's just x equals 1. All right, and the last one, I'm not going to have time to go through it. I'm just going to show you the first step, and we'll finish it tomorrow. But that was the last one. So this one's a little different because you don't have a radical by itself. I'll show you the first 2 steps. Bless you. The first step is you have to take one of these roots and put it on the other side. You've got to get one root alone. I think it's easiest to move this over there. If you want to do it a different way, you can. Now, here's the part where you have to be careful. What power could I raise this side to get rid of a square root? Yeah. Square. If you square the left, you have to square the right. The left is easy. That's done. The right is not as easy. You cannot just square each of those and say, oh, it's just 1 and then 4x plus 9, because when you square a square root, it cancels. What the right-hand side means is this. That's FOIL. You have to FOIL that out, and that's the right-hand side. 1. That's 1 times the square root of 4x plus 9. And another 1 times the square root of 4x plus 9. That's 2 of them. 2 of the square root of 4x plus 9s. And the last part is the square root of 4x plus 9 times the square root of 4x plus 9. So you could think of it like this. But when you multiply 2 square roots that are the same, the square root cancels. So all you really have is that. The square root of 4x plus 9 times the square root of 4x plus 9 is 4x plus 9. Most people get these two, but they forget about the O and the I part of the FOIL, the outer and the, F-O. Yeah, the O and the I, the outer and the inner. They forget to do those. All right, so we'll finish that one tomorrow. It's actually not bad from here, but the first part, that's usually the worst. Okay, so that's homework for tonight on 255. Okay, we'll look at that tomorrow. And remember, tomorrow is the last day of new material for the week, and we have our test on Friday.